The last thing that I want to mention right now, and I'm going to get into the real definition of this, is the far field region. And we made some allusion to the far field approximation before, and that was saying that we could neglect all 1 over r squared and 1 over r cubed field terms. But there's also an approximation that we can make in the phase argument of our radiation integral. Remember that the radiation integral has the magnetic vector potential as a function of big R is equal to mu over 4 pi. It's not always mu naught, technically, if we had an antenna that was radiating in a medium that was magnetic, but that almost never happens, so we write mu naught unless specifically instructed otherwise. And then we're integrating a volume integral over the primed coordinates j of r prime times the spherical propagation factor, e to the minus j k magnitude of r minus r prime divided by the magnitude of r minus r prime, dv prime. So in a realistic antenna problem, we have a small antenna body. That's our antenna over here. And the origin is usually inside the antenna body somewhere or very close to it. And then we have an observation point that is very far away. That's R. So our approximations for the far field approximation are going to assume that R is much greater than R prime, and R is much greater than a wavelength. Under these conditions, we can do 2 separate approximations for 2 terms in here. We're going to do one approximation for this R minus R prime magnitude term on the bottom, then we're going to do a different one for the one in the phase factor. On the bottom, we can say that 1 over magnitude of R minus R prime, that's approximately equal to 1 over R, because R prime is so much smaller than R. That's fine. However, the phase term still, because phase terms loop around the unit circle, because that phase factor keeps looping around the unit circle over scales that are small compared to R, we still have to account for that phase variation in the R minus R prime. But we can simplify it a lot. And the way we simplify it is by noticing that all of the rays from any particular value of R prime to our observation point R on the antenna body are almost parallel. That's the key point there. And because of that, if we have a point that's over here and a point that's over here, like let's say that the bottom point here is at 0 and this other point is at R prime, and they're both looking at some observation point R that is off the screen far away. What we really care about here is the difference in distance between this line and this line. And if we draw a little perpendicular line, if we drop a perpendicular down there, then we get that that difference in distance is right here. This hypotenuse is R prime. This is the angle between r and r prime. And then this length there is r prime. I'm going to name that angle psi, r prime cosine of psi. Because we remember the properties of dot products, we know that r dot r prime, whoops, too many primes, is equal to the product of the magnitudes times the cosine of the angle between them. So we can write r prime cosine psi as r prime times r dot r prime divided by the magnitudes of r and r prime. These r primes cancel out, and you get r prime dot r hat. So if I take all that and I put it back in, that's r prime dot r hat now. If I put that back in the argument of my propagation factor, I get e to the j k r minus this little length here. That's the difference between the length of these two rays. So r prime dot r hat. And then on the bottom we just got r. Putting that back in my radiation integral, I've got, remember we're going for the magnetic vector potential, A of r is equal to mu naught over 4 pi, integral over the primed coordinates, j of r prime, e to the minus jk r over r. Oh, hey, that's the spherical propagation factor, and it doesn't depend on r prime anymore, so we can move it over to the front, times e to the jk r prime dot r hat, and that's dv prime. The far field approximation is the thing that makes the radiation integral exactly the same as a Fourier transform. Without it, it's only approximately like one, but once you're doing the far field approximation, this phase term becomes a Fourier transform in 3 dimensions, because r prime dot r hat is equal to, we'll write this again one more way, then, okay, so if I'm rewriting that phase factor, I get e to the jk x prime x hat plus y prime y hat plus z prime z hat dotted with r hat. So whatever direction our observation vector is in gets dotted with this expression for a point on the source current. And this all comes from the assumption that the rays from r prime to r are parallel for all values of r prime. So that's just a simplification of how to do the radiation integral. And that's what we mean when we're talking about the far field.